Computers store all information in codes that consist of code words that have the same number of bits. Consequently, the number of unique code words in a code is determined by the number of bits. For example, if the computer uses 32 bits per code word, it can represent over 4 billion unique numbers. Consequently, when we perform calculations with the computer, we need to make sure that the calculations that we want to compute can be computed within the architecture of the computer. If we use a 4-bit architecture, and we use standard unsigned binary representation, the architecture can represent 16 unique numbers, 0 through 15. Let's look at a 4-bit architecture and discuss how we perform addition within these architectural constraints. Let's begin with a simple addition, say 4 plus 6. As you might expect, 0 plus 0 equals 0, and 0 plus 1 equals 1. These additions are straightforward and easy because we can represent 0 and 1 with a single bit. However, when we add 1 plus 1, the sum is 2, which is represented with 2 bits, 1 and 0. Therefore, we move the 1, which has a greater weight, to the next position, which has its equivalent weight. This operation of moving a bit to a position of greater weight is called a carry operation. This carry bit is then added to all bits of equivalent weight so that the sum is 1. When we implement any operation with a computer, we want to make the operation algorithmic. In other words, we want the computer to perform the same series of operations repeatedly until the operation is completed. As you may notice, we did not write the same things for every set of bits. For some sets of bits, we carried, and for some sets of bits, we did not carry. When a computer adds two numbers, it needs to create a carry-out bit for every addition of bits. So we must carry a 0 to each higher weighted bit, even if that seems a little silly to us as humans. Let's further examine this algorithm by adding 3 plus 3. 1 plus 1 sums to 2, so we carry the higher weighted bit of 1 to the next position. 1 plus 1 plus 1 sums to 3, so we carry the higher weighted bit to the next position again. 1 plus 0 sums to 1, so we carry the higher weighted bit of 0 to the next position. Finally, 0 plus 0 plus 0 sums to 0, so we again carry a 0 to a higher position. Notice that the 0 would need to be stored in a 5th bit. But since we do not have a 5th bit, this 0 will not be stored within the computer. Because we cannot store this 5th bit in a 4-bit architecture, we need to make sure that our 4-bit additions do not result in sums that are greater than 15. For example, if we tried to add 10 plus 12, we'd discover that an error happens in this architecture because we cannot represent 22 with just 4-bit binary. Instead, the number will be represented as a 6.